Hi, and welcome to our learning unit. Today we're going to discuss redundant field-installed composite design and how it achieves superior building waterproofing and contaminant protection. In today's construction environment, building envelope protection is becoming increasingly difficult. With limited land, foundations are now being built deeper, contaminated sites are now being redeveloped, and construction methodologies are now focused on constructing buildings faster. All of these factors contribute to making it very difficult to achieve superior building waterproofing and contaminant protection. In the course today, we are going to review how redundant field-installed composite systems provide the best protection to your below-grade building envelope. Hi, my name is Peter Grant, Vice President of Marketing and Sales with EPRO. For nearly 25 years, EPRO's waterproofing and contaminant barrier solutions have been installed on thousands of sites throughout North America and abroad. We are the pioneers of redundant field-installed composite design. Let's begin. The learning objectives to this course are as follows. 1. To understand the problems created by groundwater and contaminant infiltration into buildings, along with the causes of infiltration. 2. To be able to compare and contrast single-component waterproofing products with a redundant field-installed composite system. 3. You'll learn the major components of redundant field-installed composite systems, along with the components that prevent contaminant infiltration. And finally, we'll discuss a good, better, best approach that is used by redundant field-installed composite systems to scale the system to the appropriate application and project needs. The problem with groundwater and contaminant infiltration is that three main issues can arise. First, human health issues. I don't think any building owner or anybody involved in the building industry wants the occupants of its building adversely impacted because of the infiltration of contamination or groundwater. Secondly, building integrity issues. Over time, if exposed, the integrity of the building can be compromised. And finally, liability issues. If the owner does not take proactive steps when constructing the building, they may be held liable for not properly addressing any environmental challenges that were previously there. One of the first things we're going to discuss is something that's very common throughout the U.S. The breakdown of uranium over time will create radon. Radon gas is something that impacts many, many people. Personally, I don't think it's being taken seriously enough within the U.S. It is odorless, tasteless, and colorless. In the United States, it is the #1 cause of lung cancer amongst non-smokers, and according to the U.S. EPA, it contributes to close to 21,000 deaths a year. It is one of the most potent contaminants, and exposure to children or even just small exposure can lead to cancer. While radon has been around for centuries, the impact of mold inside buildings is relatively new. Buildings have become more efficient, and therefore if moisture can enter a building, it has a very difficult time exiting the structure. This can create mold infestation, and mold comes in a variety of different types. Toxic mold is obviously the most concerning, but other types of mold can even cause allergic reaction for occupants inside the structure. Personally, I've been exposed to mold inside of a home before, and it's not pleasant. One of the biggest challenges, though, is that once mold is present inside your building, it is very difficult to eradicate. The best way to control mold inside of a structure is to eliminate moisture transmission inside the building. Next, we're going to discuss methane gas. Methane gas is commonly found when developing a building over a former landfill, near a former landfill, on an old gas station, or in areas where development has occurred over dredged up material. It also occurs when building on an old oil field. Some of you might be wondering, who develops an old oil field? Well, the city of Los Angeles is in fact developed over an entire oil field. And this has created significant challenges for the building department of the city of Los Angeles. The structures you see here are examples of where methane has intruded into the building to such concentrations where just the smallest spark can in fact ignite an explosion within the building. Methane gas comes up under pressure and often under high concentrations. Mitigating methane is relatively easy, however, precautions need to be made to make sure that methane intrusion does not occur. Contaminant vapor intrusion is now becoming an issue because of the redevelopment of former industrial and manufacturing areas. These areas over time have been polluted with chlorinated solvents such as PCE and TCE, and also with petroleum hydrocarbons such as benzene. Benzene, PCE, and TCE are the driver for many of these sites, and during the redevelopment process, it's important that they're cleaned up. The challenge arises when the cost and the time needed to fully remediate a site is not very feasible. What happens is they need to leave contamination in place. And because of that, mitigation controls are relied upon in order to prevent contaminants from entering the structure. When exposed to these carcinogens over time, it can be considered to be a human health impact and is considered a significant liability to building owners. Costly investigations, remediation, perhaps reduced property values, and even shutdown of the buildings has all occurred on sites that have been impacted with contaminant vapor intrusion. Groundwater infiltration into a building can be very problematic. It can cause destruction of the building foundation and slab. It can also lead to the deterioration of building materials such as steel, wood, and insulation. In addition to disrupting the building use, it can be very visually unappealing and lead to bad odors. Compounding the issue is when your groundwater is contaminated. That can lead to the unhealthy environment of the building inhabitants. The biggest challenge is that once the building is constructed, it can be very costly and time-consuming to properly mitigate the problem. So now let's look at why groundwater and contaminants enter buildings. So you might question, why do we need to waterproof? Well, let's first look at the materials that are used to construct buildings. Concrete is most commonly used to construct buildings, and in below-grade environments, most commonly used are cast-in-place concrete as well as shotcrete. These materials are inherently porous and all concrete cracks. Shotcrete creates a significant problem because of the unevenness or the shadows that are created during a shotcrete application. It is crucial that any membrane system have a sound substrate to support the product. The challenge with shotcrete is when the voids are created and hydrostatic pressure is present, it can create significant amount of pressure on the membrane itself. One of the things that we always recommend is that the American Concrete Institute shotcrete guidelines are always followed, and that an ACI certified nozzleman is used for shotcrete applications. In addition to the concrete materials that can be used, penetrating the membranes for electrical and plumbing can also create pathways for water migration into structures. In a below-grade environment, water can exert pressure on the building foundation. Groundwater is forced into the building due to the groundwater's weight. This pressure can be significant, and water is very patient. Water will find the path of least resistance, and any deficiency in a waterproofing system will be found by the water over time. As water enters the building, you will see it come out through the building foundation walls or up through the building slab. While water migration enters into a building because of hydrostatic pressure, contaminant vapors transmit differently. They transmit based off of two different mechanisms, diffusion and advection. Diffusion is the migration of high concentration to low concentrations. Advection is flow through pressure differential. In below-grade environments, advective flow can be significant because of the temperature differentials between the exterior and the interior of the building. These flow characteristics can be exacerbated by cracks in the concrete, penetrations not being sealed, and other types of imperfections in the below-grade environment. And finally, we've discussed hydrostatic pressure, different types of building materials, as well as diffusive and effective flow into buildings. However, the reality of it, and the most common reason why water contamination might come into your structure, is simply because of human error. Most of the time, this is associated with damage to the membrane. For example, putting a nail through a completed membrane system is not a good idea. Secondly, it could be that the wrong product was installed. Perhaps the product wasn't properly rated for chemical resistance. Perhaps it really wasn't meant to be used in a hydrostatic condition. Whatever the case may be, proper material selection is very critical in keeping that below-grade environment secure. Finally, it really comes down to oversight. You can put mechanisms in place and make sure that the proper oversight is achieved, and that will drastically reduce any type of human error associated with your below-grade protection. Preventing groundwater from entering buildings is a fairly simple concept. All you really need to do is stick a barrier between the subgrade and the below-grade building foundation. So while the concept is simple, selecting a barrier can actually be difficult. In looking at the number of attributes, you need to evaluate whether the barrier is appropriate for use with contaminated soils, contaminated groundwater, and also can be used in hydrostatic conditions. It must effectively manage and prevent water migration into buildings. But most importantly, it must manage the construction process. Construction is basically organized chaos. There's a lot of things happening on a construction site. To be able to withstand the foot traffic, the rebar, and everything that's being placed over the system, it must be fairly robust. In addition to those factors, it must be able to withstand the factors that are created by nature. And it must be able to withstand time. These buildings are built not for 2 years, not for 3 years, but are in use for many years after construction. And the ability of a waterproofing product to withstand time is crucial. There are two schools of thought in below-grade building envelope protection. One is the use of a single component barrier, and the next is a redundant field-installed composite system. A single component system really relies on one technology, one line of defense in protecting your building foundation. If this line of defense is punctured or damaged in any way, the system's compromised. Next, it also relies on a lot of detailing. There can be literally hundreds of seams. Small rolls are often used, and a lot of hand detailing is required. If one detail is not done properly, the whole system can be compromised. Really, this ignores the overall chaos that occurs on a construction site. What happens with a single component system is that you're asking basically for a one-size-fits-all approach to your below-grade foundation needs. Building construction is not one-size-fits-all. Different methodologies are used, different ways of construction are used, and this can create challenges when trying to match a product to fit a specific condition. No single material can do all that's needed to create effective below-grade long-term protection. Multi-component and redundant field-installed composite systems provide a different approach. One, they're designed with the idea that construction is chaotic. There's a number of different factors that can impact the installation of a system that may or may not be in control of the manufacturer. It permits the inevitable flaw that may occur. If one layer is compromised, the whole system and the whole waterproofing integrity of the building is not compromised. Really what it does is provides the flexibility to match the application or match the product to the project conditions. With multi-component systems, multiple layers of redundancy are also built in. Essentially what's being asked is that you're asking each product to do its job. You're not trying to fit one product for a specific scenario. You're relying on all products to work together to create one goal. Leveraging the benefits of each product within one system will create a greater likelihood of success. Now we're going to look at the materials used when constructing a redundant field-installed composite system. The first material being used is a geocomposite membrane. A geocomposite membrane can serve multiple purposes in a composite system. When used as a base course on an underslab or in a vertical wall application, the geotextile side acts as a protection course against this underlying substrate. The HDPE membrane on top provides a uniform substrate for the application of a polymer-modified asphalt membrane. When used as a protection course, the geotextile faces up, the HDPE faces down. When concrete is cast onto the geotextile fabric, a mechanical bond is created between the system and the overlying concrete surface. Not only does it protect against water, it's designed to protect against contamination and methane. An upgrade to a standard geocomposite base sheet is a thermoplastic heat welded sheet. These seams are welded every 12 feet on center, and the heat welding provides superior protection against chemical impacted groundwater as well as groundwater conditions. This provides an ideal substrate for underslab applications as well as vertical wall applications, and provides the highest level of chemical resistance of any product on the market. After the application of the initial base course, a polymer-modified asphalt is installed onto the base course. This is a polymer-modified asphalt is applied at either 60, 80, or 100 mils. It can be applied to the base course or directly to a concrete wall. What it does is it creates a layer of seamless waterproofing protection. It provides exceptional bonding, elongation, and hydrophobic properties, and can even be applied to damp substrates. After the polymer-modified asphalt layer is installed, a protective course needs to go over that. There's a number of different protection courses that can be used, but this is one of the most robust. It's comprised of 3 different materials. On one side is a geotextile, in the middle is an HDPE, and on this inward-facing side is a bentonite. Bentonite provides a last line of defense if the system should ever be compromised. The bentonite will swell when it comes in contact with water, basically creating a uniform water stop across the whole system. Other protection courses are also required. The idea with a field-installed composite system is that you can interchange components based on the building conditions or based on the application type. For example, we would not use the previous bentonite on an over-excavated wall. Instead, we would use this on an over-excavated wall. This has a more robust film on one side and the bentonite on the other. The bentonite goes up against the foundation wall, and this is left to protect against any backfill. The components are almost identical, but the point is that you're using the correct material to match the specific project need, as well as the application type. It installs vertically and is hung smooth with a 3-inch overlap. There are other protection courses that can also be used. For example, this is a polyolefin sheet. This can be used on horizontal deck applications as well as below-grade over-excavated walls. The concept again behind a redundant field-installed composite system is that you can scale the system to meet the project needs. If the project does not require a bentonite application or a fully redundant system, this would be another way to add redundancy to the system without the added cost of adding bentonite. The final component in some of these systems is the use of a prefabricated drainage mat. And there's a number of different drainage mats that can be used. We use them for a number of different reasons. In some cases, we spray to the back of them, and in other reasons, we select one over the other based on the compressive strength that is needed for the project. Again, we're trying to tailor the system to meet the project needs. The idea behind a drainage mat is that there's channels behind the geotextile on each of these that will filter out any fines and allow water to flow or drain to the specified area. We've discussed the individual components. Now we need to learn how all these components come together in the field. There's a number of different applications that we need to discuss. The first is an underslab application, then how these systems are applied in over-excavated walls. Then we'll discuss how they're installed in complex shoring applications, and we'll finish up with how these composite systems can be installed on horizontal decks. We're going to begin by discussing underslab applications first. And again, we'll be progressing in a good, better, best approach. The good system is used for low-risk sites, sites impacted with vapor intrusion, sites with methane gas or radon. It begins by first installing a geocomposite base layer. This base sheet is first applied, the seams are overlapped, and then a polymer-modified asphalt is sprayed to 60 mils. Finally, a protection course, another layer of HDPE and geotextile, is applied over the entire system. When the composite system is complete, concrete is placed over the membrane. A way to increase this system is by taking everything up a level. The way that this is done is by increasing the polymer-modified asphalt from 60 mils to 80 mils, and then adding the bentonite protection course. This provides another layer of redundancy for applications that require more waterproofing protection or when hydrostatic conditions are present around the base of the slab. To move from better protection to best protection, additional layers are swapped out. In this type of condition, the best protection is required when the ultimate assembly is needed, or if project conditions require. In some cases, what this will mean is significant contamination is present, or there's significant hydrostatic pressure. To increase to the best, the base sheet is swapped out to the thermoplastic heat-welded membrane. The polymer-modified asphalt is increased from 80 mils to 100 mils, and the same bentonite protection course that was used in the previous assembly is also used in this assembly. This requires or provides the highest level of building protection in an underslab condition. One of the things that we want to review is how these are detailed. The detailing of these systems is very critical. As you can see here, all of the types of materials are used when trying to seal around a pipe penetration. What's really key to these composite systems is that all of these systems are used continuously underneath the slab, around the vertical walls, and basically in any type of condition. How a pipe penetration is done under slab is the same way it's done in other areas as well. The idea is that while these systems may appear to be complex in a drawing, the reality of it is that they're very simple to install. For over-excavated walls, we're going to follow the same approach: good, better, best. On below-grade vertical walls, a number of steps need to be taken prior to the first application of polymer-modified asphalt. All concrete and form-curing agents must be removed, the surface must be cleaned, all patching must take place, and reinforcing any form tie holes must also be completed. After the concrete surface has been properly prepped, a 60 mil polymer-modified asphalt is sprayed directly to the below-grade foundation wall. A mechanical bond is formed between the polymer-modified asphalt and the concrete surface. Then a protection course is applied, followed by a drain mat. The drain mat and the protection course help protect against backfill as it occurs during the construction process. A better approach is to, again, by increasing various mil thicknesses and changing out different materials. From going to a 60 mil membrane, or beginning with a 60 mil membrane, we then transition to an 80 mil membrane. We also increase the thickness of the polyolefin sheet from 10 to 15 mils. Finally, a different drainage course is used, one that has higher compressive strength. When moving from better protection to best protection, the next step is fairly easy. The same 80 mil polymer modified asphalt is applied to the wall. However, instead of just using a polyolefin protection course, the bentonite composite membrane is installed with the bentonite facing the polymer modified asphalt. The drainage course is then applied up against the bentonite and backfill occurs. This provides the best level of protection for a below-grade foundation wall. Detailing of penetrations are critical and can be done in a number of different ways. Here's an example of how a penetration is sealed. What's slightly different than an underslab penetration is that all the detailing occurs on the concrete surface. Shoring applications are becoming more prevalent. In urban environments, there's little ability to over-excavate land to apply waterproofing to the positive side of walls. Instead, they're applied on the negative side. What this means is that they shore up the land in the surrounding areas and apply the waterproofing from the outside in. Different shoring methodologies can drastically impact how a waterproofing system is installed. This is where a redundant field installed composite system really shines. Having the ability to interchange the different system components to match the project-specific needs really give project teams the ability to match the system based on the performance requirements. We're going to follow again the good, better, best approach. Good protection is ideal for applications where there's very little risk. Ideal waterproofing protection for structures that do not have significant water or significant amount of contamination. A high-density polyethylene drain mat is first applied to the shoring wall. While in the detail it shows that this is wood lagging, this can be applied to a wide variety of different shoring applications. The drain mat is secured onto the drainage composite. The drainage composite is applied to the shoring wall, and 60 mils of polymer modified asphalt is applied. In this unique situation, the concrete is then cast up against the waterproofing membrane or instead of concrete being cast, it can be shotcreted up against the membrane system. What happens is the membrane or the waterproofing system becomes fully integrated with the below-grade foundation wall. When project conditions require it, better protection can be achieved in a number of different ways. Better protection may be required when excavations are deeper, post-tension foundations are used, or shoring walls have less than ideal substrates. The upgrade occurs in a number of different ways. One, the drainage course is swapped out for one that has higher compressive strength. Next, a base sheet is applied to provide a uniform substrate for an 80 mil application of polymer modified asphalt. The final redundant bentonite layer is then applied over the polymer modified asphalt to provide a triple component protection to the below-grade foundation wall. Shotcrete or concrete can then be applied directly up against the foundation wall. One of the advantages of a geocomposite bentonite as the last layer of this system is the geotextile faces outward, meaning concrete is directly applied to the geotextile surface. This means that a mechanical bond is formed between the concrete wall and the waterproofing system. When moving from better to best, other subtle enhancements are also made. These are ideal for fully tanking applications or applications where you're dealing with high levels of contamination. In lieu of the base course, a heat-welded base sheet is used. The same layer or same thickness of the polymer modified asphalt is also used, and the same bentonite layer is also used. Really, all that changes from going from better to best is the use of a thermoplastic heat-welded base sheet. Here's a detail of a penetration or shoring condition. You'll notice that it's very similar to how an underslab penetration was sealed. This is our goal. With a redundant system, there's a lot of different parts, but if we can keep the application process consistent, it makes installation easy. It also makes oversight easy as well. The same kind of detail that's used on pipe penetration is also used on a tieback, soil nail, raker, or any other type of protrusion that you may encounter on a shoring wall. The key to a successful installation is the transitioning. Transitioning between the horizontal and vertical plane is critical. This is where most of your leaks occur, and this is where we need to have maximum redundancy. You'll notice that the underslab membrane continues up the vertical face of the wall. The prevalence of shotcrete makes this transition detail very difficult. It is very important that proper consolidation occurs along the base of the foundation wall to remove any pockets or voids that may compromise the waterproofing system. One of the ways that this is handled in a redundant field-installed composite system is another layer of redundancy is added. You'll notice that a purple line has been added. This is basically another triple layer of protection. It is a layer of bentonite, 20 mil HDPE, and another layer of bentonite. This provides ultimate protection in most critical areas. The transition from the underslab to the vertical wall is critical. Equally as critical is the transition from the below-grade waterproofing to any deck or horizontal waterproofing above grade. This can be a number of different things. Deck waterproofing can be applied to split slab applications, plywood substrates, green roofs, pedestal and paver systems. There's a lot of endless possibilities and a number of different configurations. This is where a redundant field-installed composite system can really shine, being able to scale the system to meet the specific application need. These systems must be detailed correctly and tie into other waterproofing needs. Where a composite system makes a lot of sense is that it can also provide a single source warranty for the building owner. When you're able to tie in the below-grade waterproofing and the deck waterproofing, the building owner is provided greater assurance that one manufacturer can handle anything that might happen in the future. Horizontal above-grade waterproofing has a lot of different applications. Whether it's a plaza deck, pedestal and paver system, split slab application, different needs are required. In a good, better, best approach, this makes a lot of sense for using a composite technology. For smaller applications such as balconies or planters or low traffic decks, a simple 60 mil application of polymer modified asphalt, followed by a protection course and a drainage mat, will meet most projects' needs. However, in larger applications where you're dealing with most podium applications with pavers or most split slab applications, more redundancy and greater protection is needed. This is achieved by installing a much thicker system. To best accomplish this, what we do is we significantly increase the layer of polymer modified asphalt. This is a three-step process. It begins by applying a 60 ml polymer modified asphalt latex membrane to the concrete substrate. It is then followed by a reinforcement fabric and a final layer of 60 ml polymer modified asphalt. When complete, this is a 120 ml reinforced polymer modified asphalt membrane that's fully bonded to the substrate. A 15 ml polyolefin protection course is placed, followed by a drainage mat if needed. When moving from better to best protection, we again modify the system. We begin by the same 120 ml reinforced polymer modified asphalt, but instead of using a polyolefin plastic sheeting, we move to a heat-welded 16 ml thermoplastic sheet. This provides again the highest level of protection that we can offer. A drain mat is then applied over if needed. Redundant field installed systems, like any other system, require proper detailing. In this case, we're looking at a drain detail. It is important that all drains are properly detailed. All flashing and counter flashing on termination edges are also done in compliance with manufacturer recommendations. Now we're going to discuss some project examples of how redundant field installed composite systems are applied in the real world. Again, the concept behind redundant field installed composite systems is the ability to scale the system to meet the project needs. For deep, complex foundations being built into the water table, ultimate protection is required. What makes this foundation complex are the number of rock anchors that are used to secure the slab. The rock anchors are used to secure the slab due to the high amount of hydrostatic pressure. What makes this difficult from a waterproofing standpoint is that these are all penetrations in our system. The detailing needs to be perfect. Around each one of these penetrations, if the detailing is not done perfectly, leaks will be visible inside the basement. For this typical application, or in an ultimate protection environment, a 16 ml thermoplastic base sheet, 100 ml application of polymer modified asphalt, and a bentonite protection course provide an ultimate level of protection. While some project conditions require ultimate protection, there are other conditions that do not. In this particular case, a prudent owner wanted a higher level of waterproofing protection despite the foundation not being subjected to hydrostatic pressure. The other caveat with this particular project, though, was that there was contamination present. So not only did they need to prevent any water intrusion, but they needed to also prevent the infiltration of any methane gas. The way this was achieved was by increasing the polymer modified asphalt layer and also incorporating bentonite. This was done under slab as well as the vertical shoring walls. This provided the level of confidence to the owner that their building was safely protected. Redundant field installed composite systems also allow a building owner to pick the perfect product for the perfect project conditions. And this is a good example. Ultimate protection was not required on this site. It's a rather shallow foundation, but they also encountered shallow groundwater. In addition to shallow groundwater, contamination was also present. There is no need to install a catalytic type of approach or an ultimate level of protection, but a medium level of protection where the polymer modified asphalt latex was increased and a bentonite protection course was used, provided the owner exactly what they needed to meet the project conditions. Lower risk also means lower redundancy. In this particular case, an underslab membrane was not required. In order to provide adequate waterproofing protection, all that was needed was an application of a redundant system to the below-grade shoring walls. To achieve this, a drainage mat was fastened to the shoring wall, and 60 ml of polymer modified asphalt was then applied to the drainage composite. Upon completion, shotcrete was applied directly, and the shotcrete foundation wall fully bonded and was fully integrated with the waterproofing system, thus creating just the right amount of waterproofing to meet the project needs. There are a number of considerations when choosing a manufacturer. First, there are things you should expect. Do they have extensive experience and proven capability? Do they offer design experience? Can they complete specifications, details, and drawing for your specific project? Are there approved applicators that are approved to install that particular product for your specific project? An additional and a very important consideration is whether the manufacturer can scale the system to meet this project's specific needs, or whether the manufacturer tries to sell a one-size-fits-all approach. And finally, warranty. Warranty is a very critical component. The ability and willingness for a manufacturer to support their product in case anything were to go wrong in the future is very important. There are a number of things to look for in a warranty program. Manufacturers offer a number of different warranty types, but the best warranty available is a no dollar limit labor material warranty. This warranty is non-prorated for the term of the warranty and will warrant that the manufacturer will stand behind the workmanship as well as the integrity of the material for the warranty period. It is not easy to achieve no dollar limit warranty status, but there are strict guidelines provided by the manufacturer and a framework that is used to help coordinate the installation of the product. Overseen by a third-party certified inspector, this will ensure that the product is being installed correctly and a warranty can be achieved. We've learned a number of things today. Let's review some of the key points. Water and contaminant infiltration into a building can be harmful to the health of building occupants and hazardous to building materials. Construction methodologies, building materials, site-specific conditions, and human error all work against us when trying to protect a building from water ingress and contaminant vapor. Single-component waterproofing systems do not have the ability to meet the needs of modern-day construction. Redundant field-installed composite systems, however, provide the ability to scale up or scale down the system in order to meet the project-specific needs. Finally, selecting the right manufacturer and having a premium full coverage warranty provides ultimate protection to building owners. Thank you for participating in our course today. If you'd like to learn more about redundant field-installed composite systems, please feel free to visit our website, eproinc.com. You can either call us or fill out a Contact Us page on our website to learn more about the systems that we offer. Thank you again.